In this video, we'll see what are the built-in data types in C programming language. First of all, we must always remember that the internal representation of any data type, whether it is built-in or user-defined data type, it is always represented in binary format. Always in binary format. I have seen number of students asking how alphabets are stored, capital A, B, C, D, etc. How symbols are stored, how decimal numbers are stored. Remember, whatever is there, everything is stored in binary format. So, all built-in data types are stored in binary format. The only interpretation makes it integer. If there is a bit pattern, how do you interpret it? Whether it is you want to treat that bit pattern as integer or real number or character, etc. It depends on the number of bytes and method used to access the memory. So same bit pattern can be treated as integer or a real number or a character, as the case may be. There are three basic built-in data types in C language. One is integer, another is real number, and the last one is character. So integers, real numbers, and characters. Now, here the reserved keyword for integers is int, int. One of the integer types, it is int. And it usually indicates the natural size of an integer on the machine. And its variants are int, of course, it is short, it is also a type of integer. Long is also an integer, and long is also an integer. So these are the variants of integer. Reserved keyword is int. So these are also keywords, short, long, and long, of course. And this int is actually signed. So short is also signed, long is also signed, long is also signed. By this we mean we can represent both negative and positive numbers, negative and positive integers. And compilers are free to choose the size of an integer for their machines. So there is no restriction as per this standard. But I have not seen any compiler in which any integer is of less than 16 bits in size, that is 2 bytes, at least 2 bytes. All compilers have, C language compilers use 2 bytes at least to represent an int. The restriction is the size of short can be at the most equal to size of int, which can be at the most equal to size of long, otherwise it has to be less than that, size of long. Similarly, long cannot be greater in size than long. So at the most, the size of long and long in a system would be same at the most. Now various sizes which I have come across. Turbo C 3.0. What was it? It was 16-bit compiler for 16-bit MS-DOS for 16-bit machines. So short, int, long, and long. They were of 2 bytes, 4 bytes, and 4 bytes respectively. What does it mean? In case of Turbo C 3.0, short and int were of same size, that is 2 bytes. So it means there was no difference. And long, both were of 4 bytes. It means no difference. Whereas in case of GCC, which was 32-bit compiler for 32-bit Linux for 32-bit machines. So their short was of 2 bytes, int was of 4 bytes, long was also of 4 bytes, but long was of 8 bytes. Similarly, Visual C 6.0, which I have worked on, these numbers which I have tested myself, these are the numbers. So Visual C 6.0, 32-bit compiler for 32-bit MS-DOS for 32-bit machines. So short was of 2 bytes, int was of 4 bytes, and long was of 4 bytes, whereas I found long was illegal. It means Visual C 6.0 does not support long. GCC 64-bit compiler, which is currently being used, it is 64-bit compiler for 64-bit Linux for 64-bit machines. There you would find short is of size 2 bytes, int is of 4 bytes, long is 8, and long is of 8 bytes also. So here long and long have no difference, they are identical. Short is of 2 bytes and int is of 4 bytes. Now there is a term called short int, long int, and long int. These three terms, they mean short, long, and long only. It means short int and int both are same. Short int and short are same. Long int and long are same. Long int and long they are same. And that is why in such cases int word is dropped. So if you want to declare a variable of type int, you declare it as int. Short, then you say short int x, suppose, or short x. So people normally drop the int keyword in such situations. What are the ranges? If an int or short or whatever data type you are choosing, if it is of 2 bytes, you can represent minus 32,768 through plus 32,767, or minus 2 to the power 15 through 2 to the power 15 minus 1. These numbers you can represent in 2 bytes. Using 4 bytes, you can represent this range, huge range, which is nothing but minus 2 to the power 31 is the minimum, and maximum is 2 to the power 31 minus 1. If it is of 8 bytes, it is this huge integer which you can represent. It means 64 bits. Or you can say minus 2 to the power 63 through 2 to the power 63 minus 1. So if number of bytes are 8, it means 64 bits. So reduce it by 1, so 63. So minus 2 to the power 63 through plus 2 to the power 63 minus 1. Now normally we can make use of a qualifier unsigned. So if we say we can use unsigned, we can make unsigned short, unsigned int, unsigned long, and unsigned long. So if we use the qualifier unsigned, it means we don't want to represent negative numbers. So then it will represent 0 as the minimum number representable, and maximum number would be depending on the number of bytes. So for 2 bytes, the smallest number integer would be, positive integer would be 0, maximum would be plus 65,535, or you can say 0 through 2 to the power 16 minus 1. For 4 bytes, 0 through 2 to the power 32 minus 1. And in case of 8 bytes, it will be 0 through this huge number, or 0 through 2 to the power 64 minus 1. Now real numbers. Now we can represent real numbers using two mechanisms. One is fixed point and next one is floating point. What happens is, using 2's complement, it is possible to represent numbers on both sides of 0 on number line. That is, using fixed point notation, 2's complement, you can represent same number of bits you can use to represent positive number and negative number as well. So after 0 point, we can use some bits to represent the fractional part. So assume a fixed point, fixed binary point. It is also possible to represent numbers with fractional part. So for example, 1 0 binary point, so I will say dot 0 1. What does it mean? So on the left hand side we know this place represent 2 to the power 0, this place represent 2 to the power 1. So here this is 2 to the power 0, 2 to the power 1. So this becomes 0, its contribution is 0, and its contribution is, this place's contribution is 2. So we add these two, so integral part is 2. Now here on the right hand side, the exponent of 2 keeps on increasing as far as magnitude is concerned, value is concerned, but it is negative. So this place represents 2 to the power minus 1. This place represents 2 to the power minus 2. So this is 0 multiplied by 2 to the power minus 1, that is 0. And this is 1 multiplied by 2 to the power minus 2, which is equal to 0.25. Add these two. So this is 2.25. So 1 0 binary point 0 1 represent 2.25. But in this case, in such representation, fixed point representation, that is the location of place of binary point is fixed. What is the limitation? Very large numbers or very small fractions cannot be represented. That is the limitation. So to solve this problem, scientific notation or floating point notations are being used for real numbers. In such representation, what happens? For example, I have this number, okay, 4,56,000 or 456,000. This can be represented as 456 multiplied by 10 to the power 3 or 0.456. 0.456 can be written as 456 multiplied by 10 to the power minus 3. What has been done? The decimal point has been shifted to a convenient location and exponent of 10 is used to track this decimal point. That is why floating pointer. Something like we used to do in slide rule, in which the place of the pointer would remain same whether it is 10 to the power 1 or 10 to the power 2 or 10 to the power 3. Place would remain same, and you need to you can say estimate what would be the exponent of 10. We can represent very large number as well as very small numbers using only few digits in floating point representation. This can be applied to binary numbers also, as in computers the numbers are always stored in binary format, as I have already told you. Generally we can represent a number as this, plus minus m multiplied by r to the power plus minus e. So m is mantissa or significant, r is radix or base, and e is exponent. Now base is implicit because in case of binary, base is implicit. So that is why, and it is same for all numbers on a machine. So that is why it is not stored separately. So there is no place in a 32-bit representation, maybe 32-bit floating point number. There is no place to store base. It is assumed it is 2. This representation can be stored in a binary word, that is 32 bits. So now you can see here, bit 0, this is used to represent sign. If this is 1, the mantissa is considered to be negative, and if it is 0, the number is considered to be positive. Then bits 1 through 8, this 1 through 8, these 8 bits, this is referred to as biased exponent. Biased exponent. And bits 9 through 31 represent the mantissa. So here it is sign of the mantissa. Bits 1 through 8 biased exponent, base is not stored, and bits 9 through 31, it means these bits from here up to including this. These bits represent the mantissa. So as I told you, if sign bit is 0, mantissa is positive, otherwise it is negative. Okay. Now exponent is a fixed. From what is exponent? A fixed value called the bias is subtracted from the field to obtain the correct exponent value. So how many bits are there in exponent? 8. So 8 bits can represent 255, maximum number. All bits 0. 8 bits, these 8 bits are 0, then it is 0. All bits are 1, it means 8 ones, that is 255. So here 8 bits of exponent yields numbers 0 through 255 with a bias of 128. With a bias of 128, if we subtract 128, correct values of exponent are in the range minus 128 through plus 127, both inclusive. And as I told you, the base is assumed to be 2. So the exponent is between minus 128 through between minus 128 and plus 127, both inclusive. Real numbers are generally normalized. Generally, they are normalized. A normalized number is in the form. What do they do? Plus minus 0, binary point I am talking about here is 0.1 and so many b's multiplied by 2 to the power plus minus exponent. B is a binary digit 0 or 1. Okay. B is binary digit 0 or 1. The leftmost bit of the mantissa has to be 1 always. Okay. For normalization, this bit, the bit which I have represented here, this one, this bit. For normalization purposes, this bit has to be 1 always. So if leftmost bit of mantissa has to be 1 always, then why to store it? Because we know it, that it is always going to be 1. So it is not necessary, or rather it is unnecessary to store. Hence, in 23-bit mantissa field, we can store 24-bit mantissa with a value between 0.5 and 1.0. In such a 32-bit format, following floating point numbers can be represented. I have written here, we can represent these numbers. Okay. So negative numbers between, you can say this number, minus 1 minus 2 to the power minus 2 to the power minus 24 multiplied by 2 to the power 127. This is the negative number, smallest negative number which we can represent, and the biggest negative number, floating point number, minus 0.5 multiplied by 2 to the power minus 128. So negative numbers we can represent between these. Positive numbers between these two values, 0.5 multiplied by 2 to the power minus 128. This is the smallest positive number which we can represent, and this is the biggest positive number which we can represent is 1 minus 2 to the power minus 24 whole multiplied by 2 to the power 127. But remember, we are still representing 2 to the power 32 numbers only, as the word size is still 32 bits. As we move near center of the number line, these represented numbers come closer. What does it mean? It means more and more number can be represented exactly when we move towards 0 or the center of the number line. And as we move farther away, the represented numbers spread farther apart. It means between two exactly representable numbers, you will find less number of numbers which can be represented exactly. Okay, and that is why I always tell my students, you should always remember that we should never rely on the results of floating point operations, as not all numbers can be represented exactly. So it means it is possible that more than one numbers can be represented using same bit pattern. So two values or more than two values can be represented identically. So for small numbers which are you can say somehow which can be represented as the sum or sum of numbers which are power of 2. they can be represented exactly, not others. For example, 0.5, it can be represented exactly because 0.1, binary point 1, it is 0.5. Then 0.01, which is 2 to the power minus 2, which is 0.25. Then 0.001, which is 0.125, etc. So those numbers can be represented exactly, otherwise the number cannot be represented exactly using this floating point representation. The following ranges are not representable, like negative overflow. We call those numbers negative overflow. It means any number which is less than this number, it cannot be represented. So we call it negative overflow. Okay? And negative underflow, negative numbers greater than this number. Any negative number which is greater than this, it cannot be represented. So we call it negative underflow. Positive underflow, positive numbers less than this, we call it positive underflow. Positive overflow, positive numbers greater than 1 minus 2 to the power minus 24 multiplied by 2 to the power 127. So that is called positive overflow. 0, in all practical systems, there is a special bit pattern to represent this value. Now, in case of C programming language, float is the reserved keyword for floating point single precision numbers. Double is floating point double precision, and long double is extended floating point in C language. And the precision of float has to be less than or equal to the precision of double, which has to be less than or equal to precision of long double. And this precision is offered is also compiler dependent. Now, in case of Turbo C 16-bit Turbo C 3.0, which was for MS-DOS, float is of 4 bytes, whereas double is of 8 bytes, and long double is of 10 bytes. This one, 4 bytes, 8 bytes, and 10 bytes in case of Turbo C 3.0. Whereas 32-bit Visual C 6.0, which was for MS Windows, float is of 4 bytes, double is of 8 bytes, and long double is also of 8 bytes. In case of 32-bit GCC Linux, float is of 4 bytes, double is of 8 bytes, and long double is of 12 bytes. In case of 64-bit GCC Linux, 4 bytes for float, 8 bytes for double, and 16 bytes for long double. So huge precision. Now, for sophisticated numerically oriented programs, the IEEE, that is Institute of Electrical and Electronics Engineers, they developed a standard in 1985 known as IEEE 754. To ensure the portability, that standard is independent of the hardware, any hardware. This is widely accepted and adopted, and it is used in most of the modern processors and coprocessor. This standard defines standard for both 32-bit single precision and 64-bit double precision formats. In both cases, both formats, bit 0 is sign bit. 32-bit format has 8 bits of exponent, whereas 64-bit format has 11 bits of exponent. Here also the base is assumed as 2. But the standard defines two more extended formats, single and double. The extended formats have extra bits in the mantissa field as well as exponent field for improving precision and as well as the range. But remember, exact format is implementation dependent. Now, as per the 754 standard, now you can see here, number of bits float, that is single precision, 32 bit. Double, 64 bit. If it is, so this is the double precision, number of bits is 64. And single extended format, the number of bits would be greater than or equal to 43. And in case of double extended, greater than or equal to 79 bits. In all these, mantissa bits are different. For example, in normal, as we have just discussed, single precision, that is floating point number, float, mantissa bits are 23. In case of double, mantissa bits are 52. Exponent bits are 8 and 11 respectively. Exponent bias is 127 in case of a float and 1023 in case of double as far as C language is concerned. The minimum value of minimum exponent is minus 126 and minimum here is minus 1022. Maximum exponent is 127, okay, 1023 and so on. The number of values, these number of values we can represent. Number of exponents, 254 here, 2046 here, number of fractions and so on. You can see decimal number range is 10 to power minus 38 through 10 to power plus 38. Here it is 10 to power minus 308 through 10 to power plus 308. Okay, that is huge range. And this X means cross I made, this has not been, these things have not been specified. Now the next built-in data type is in C is character. That is reserved keyword is char, C-H-A-R. Actually, strictly speaking, char is 1 byte integer in C. Okay. We can make use of it as a single byte integer, and in some other video, perhaps next video, I will demonstrate how it can be used as 1 byte integer. It can hold values from minus 128 through plus 127. As character, it cannot take on any value below 0. Whereas by default, byte value of a char, minimum is 0 and maximum is 127 when that byte is being used as a char. Now there is one qualifier, unsigned. So unsigned char or 8-bit ASCII codes, for them, for it, minimum value is 0 and maximum value is 255. That is all in this video. Thanks for watching.